This is probably a foolish plan, but I'm going to try to speed run through my semester one review before class starts in 15 minutes. So we'll see how far I can get. So we're going to show there are two geometric sequences. Second term is 9. So we know that G2 is 9. And the sum of the first three terms is 91. So G1 plus G2 plus G3 is 91. Okay, that's great. So then I know that I can write G1 as G2 divided by the common ratio. 9 is the second term. And G3 is G2 times the common ratio, and that's 91. And I realize that I don't need to write G2 because we know G2 is 9. So we actually have 9 divided by R, 9, and 9 times R is our three terms. I'm going to multiply everything by R to get this equation, which is now a quadratic in terms of R. And I'm going to subtract the 91R and write my terms in order. So 91 minus, or 9 minus 91 would be that. And I don't know why they don't add up. Okay, so then I just have a quadratic equation. So opposite of b plus or minus b squared minus 4ac all divided by 2a. So the way that you can figure this out using a calculator if you want, and then the way that you figure out the fourth term of each sequence is it's just g2 times r squared. Okay, and so that's just going to be 9 times r squared. You can do the rest of it. Don't have time to go through those details. Number two, ABC make an arithmetic sequence, BCA make a geometric sequence. They add up to 36. So let's write our clues. A plus a common difference is B. B plus a common difference is C. And that's what it means to be an arithmetic sequence. If I put those two ideas together, that means that B minus A equals C minus B. Try to ignore that I wrote the plus sign twice there. Now we know that B, C, and A form a geometric sequence. So B times R is equal to C. C times R is equal to A. If you put those two ideas together, that means that C divided by B is equal to A divided by C. And if you cross multiply, that means that C squared is equal to A times B. Our last clue is that the three numbers add up to 36. So A plus B plus C adds up to 36. Great. So what can we do here? We can do some different substitutions. I guess if we substitute here by adding, let's see, let's isolate C here. So if we look at this, we know that I can add B to both sides. So I get C equals 2B minus A. And if I look at my other clue here, it says that C squared is equal to AB. So I'm going to square both sides there. And if I square this left side, I get 4b squared minus 4ab plus a squared. And that has to equal a times b. And I can then, I guess, subtract ab. 4b squared minus 5ab plus a squared is equal to 0. Okay, let's see how we can use that information. The other thing I could do with the c value is substitute it into my 36 equation. So now I know that a plus b plus c, which is 2b minus a, is equal to 36. Oh, now we're getting somewhere. It's positive a, negative a. So 3b is 36. So that means b has to equal 12. So if we know b has to equal 12, now we can use our clues here. And we know that they need to be evenly spaced around 12 because they're an arithmetic sequence. So let's see here. Great. So then I know that C is equal to 2B minus A. So C is equal to 24 minus A. And I also know that C squared is 12 times A. I can go back down to this equation down here at the bottom where it says 4 times B squared. So 4 times 144 minus 5AB. So that's going to be 60 times A plus A squared is equal to 0. And then that can give me the value of A if I use the quadratic equation on it. And once I have the value of A, I also have the value of C. I'll have two different possible answers. So because of the plus or minus, so just double check them and see which one works. Okay, I'm going to leave it there just for the sake of time. All right, now we've got a proof about combinations. So we're proving this. I'm going to try to just prove it directly. N choose 2 can be written like this. N factorial, n minus 2 factorial, 2 factorial. The other one is n minus 2 choose k minus 2. So n minus 2 over, then you do the top minus the bottom. That's what I did with n choose 2 is I did n minus 2. So here I'm just doing n minus 2 minus k minus 2 factorial times k minus 2 factorial. And my goal is to get n choose k and k choose 2. So the first thing I'm going to do is deal with this nasty thing here, distributing the negative. So copy the first piece down again. Copy most of the second piece down again. If I distribute the negative, I just get n minus k because the minus 2's cancel each other out. And then all I have to do to finish this proof is just do some switching. I want it to say n choose k. So I want this term to go right there because the pieces on n choose k are going to be uh, um, n factorial on top and then n minus k factorial on the bottom. And then the other one that I want is k choose 2. Well, I noticed that I actually have an n minus 2 factorial on both pieces that can cancel out. And so what I need is somehow to make this into k choose 2. So let's write down where we're at so far. We've got n factorial over n minus k factorial. I'm going to move the 2 over here because it looks like it fits with the other piece a little bit better. And over on the second fraction, I have 1 over k minus 2 factorial times 2 factorial. And now what's the only missing piece? The only missing piece is my n choose k needs a k factorial on the bottom. My k choose 2 needs a k factorial on top. So I just multiply the whole thing by k factorial over k factorial, which is just a crazy version of 1. And I've proved the statement. This is n choose k, and then this is k choose 2. Great. All right. Here's another proof. Prove that n cubed plus 2n is a multiple of 3 for all integers that are positive. Okay. So this looks to me like an induction proof. So let's start with n equals 1. That would be 1 to the third plus 2 times 1, which is 3. And that is indeed a multiple of 3. 3 times 1. Check. Now we're going to assume that n cubed plus 2n is 3 times k for some integer. That's what it means to be a multiple. And then we're going to consider the next n value like this. And we're going to multiply it out. N cubed plus 3n squared plus 3n plus 1 plus 2n plus 2. By the way, all I did there was I just thought about Pascal's triangle like that and read off the coefficients. That's your binomial expansion. Okay, that's weird. Well, let's see what we've got. I know that this piece plus this piece right here is the induction hypothesis. So I know that I can replace the induction hypothesis with 3k. So let's do that. We've got now 3k plus 3n squared plus 3n, and I notice that 1 plus 2 is equal to 3. So I have a plus 3 on the end for the constant term. And this is equal to 3 times k plus n squared plus n, which equals 3 times, let's just use another letter, m, for some integer m. So it is proved for all values of n. And that is an induction proof. N equals 1, induction hypothesis, consider the n plus 1th case. I'm realizing that I'm not going to get through more than chapter 1 in this video, and that's great. I'll just stop it after this chapter 1 thing, and then we can talk about the other chapters in other videos. All right, so number 5, the coefficient x squared in the expansion of this is 495. So let's look at the expansion of 1 plus 3x to the nth. Okay, so that would become 1 to the nth plus n choose 1 times 1 to the n minus 1 times 3x to the first. I'm just using the binomial expansion. Then you have n choose 2, 1 to the n minus 2, 3x squared plus blah, blah, blah. Each time you have your combination coefficient, your n minus k, and your k. So a to the n minus k, b to the k. What do we know? We know that this right here has a coefficient of 495. So that piece equals 495x squared. So n choose 2 can be written like this, just like I talked about previously. 1 to the n minus 2 is irrelevant. 3 squared is 9. I can get rid of the x squareds because I only care about the values of n. And then I have, let's see, I guess I can divide by 9. And so I have n factorial, n minus 2 factorial times 2. 9 goes in there 54 times, I think that's right. Because 9 times 50 would be 9 times 5 is 45, and you have 45 left over. So 55 times. Yeah, because it's like, yeah, that makes sense. 55 times. And so then if I multiply, let's see, if I cancel out the factorials, then I'd have n times n minus 1, because I cancel out all of the n minus 2 and below terms. And 2 times 55 is 110. So n times n minus 1 needs to make 110. So n squared minus n minus 110 makes 0. So I have to do n minus 11 and n plus 10. And so my two values of n are 11 or negative 10. But it's binomial, so only the positive term matters. So there you go. I'll pick up with the rest of the review when I get a chance to do that.